Alright, another draft physics video presentation. Yes, it's a recording. This is one of Sean Carroll's biggest ideas in the universe and quantum mechanics, and it's like the whole group of subjects spent space and time warping and all this other stuff. This is a transition in physics from the idea that there was this clear chain between causes and effects, and that you really didn't have effects without causes, and you didn't have magic in the universe, that it was something you could trace, was always responsible. You had to have heat in to have heat out. You had to have energy in to have energy out. You had to have movement in to have movement out. This kind of order was sort of observed by the physicists. Around the same time they were figuring out God was a really dumb idea, a bad theory. And, evolution was on the horizon as a theory, and lots of things happening. And, in my opinion, the worst thing happened to physics. It just decided to go with the religious story instead of the hard mechanical, force you to explain it thing. They allowed a bunch of random and, things are uncertain about where they are in the universe or what they're doing. There's all these little mysteries out there, and that's all quantum mechanics is. It's almost impossible to define the term quantum mechanics. Does it mean entanglement? Does it mean spooky action? Superluminal, and worst of all, things don't have a position and a momentum. They're amorphous. They're not definable or describable. They're doing things for no reason. They wobble because they feel like wobbling, not because something forced them to do it. So anyway, we'll play some of this in terms of his description of why it was just so obvious that we had to take this silly turn as human beings to believe in this fake story, instead of going with the evolution thing. We were headed on the evolution path, a way of looking at physics that was just as clinical and cold and unhuman friendly as evolution, and they just wouldn't take that path.
Minus some mathematical details. And I don't want to be too historical about it. We've never been very historical in these lectures, but we can be inspired by history. So I'm going to move into quantum mechanics in a sort of pseudo-historical way. And
yeah, whatever that means. I'm going to fudge the truth, whatever.
The reason for doing this is because quantum mechanics is so radical, is so different. It's such a big break from the previous way of doing physics that it really is important to motivate it, not just to state what is going on. Unlike
to motivate it. So whatever that would mean, right, is to... it's all jump to conclusion stuff, so it's all jumping the evidence. That's my primary argument here, is that physics, that's the error, is they jump the evidence. They put cart before horse kind of obvious thing, and that's, by even the scientific method, that's against the scientific method. So you can't do good science that way, and that's all they did. They forced an answer when they weren't ready for an answer.
Special relativity, where I just sort of told you the answer, in quantum mechanics, I would really like to see why that is what the answer apparently is.
So apparently, he says, almost pejoratively, because there's no will to even have a conversation about how you're wrong, how your evidence sucks and is incredibly weak.
And then, maybe you'll be empowered to think about other ways that it could be. However, I'm not going to stick to the actual history of quantum mechanics too much. It's too rich, too interesting, too complicated. There were all these brilliant minds.
Yeah, whatever. No, it's too much of an unexplainable folly, The whole idea of Einstein getting the headline for a really crappy experiment and getting a headline saying Einstein's right about everything when it only, even if it proved one thing, it didn't prove everything.
Doing with each other. We're going to do a simplified version of quantum mechanics. And, the reason for all this throat clearing is...
I have this sped up. Yeah, so the throat clearing is the apprehension and being declarative. The reason why I have to be fudgy about this, is what he's saying, is because it is all fudgy and sketchy and sloppy. Doesn't make science look very good, because this isn't a very good scientific method you use to draw these hard conclusions about reality.
Quantum mechanics is special in the whole world of physics, in the whole set of physical theories ever invented. Everything we've been talking about up till now.
Yes, it's special in the sense that it is a real defining line between religion and science, and you decided to turn physics into a religion. And that's all that can be said. That's an accurate enough statement.
Has been in the context of this classical paradigm for doing physics.
Yeah, the classical paradigm is that you analyze the evidence, you scrutinize it, you pick at it until you get the right answer. You don't just jump to a conclusion.
Handed down to us by Isaac Newton and others, quantum mechanics is a replacement for classical mechanics. No one before the 20th century thought that classical...
Well, it doesn't replace much, frankly. It just replaces the solid idea. So, again, it doesn't replace all the discoveries of the past and all the 2 + 2 = 4 kind of stuff. It it replaces in the sense that it adds stuff like, well, let's do the square root of -1 and think that's a rational thing to do. I don't know.
Mechanics would need to be replaced. It was just working so well. Everyone thought it was just going to be a matter of figuring out what is the specific version of classical mechanics that we would need. So quantum mechanics comes along. It tells us something completely different about the world. And
it tells us something completely different about the world. It asserts something completely different about the world. So we went from a mechanical world to a non-mechanical, and then you called it quantum mechanics, which is basically saying not mechanical mechanics. That's what it's really saying, not mechanical mechanics. I mean, it's an oxymoronic counter statement.
That thing is so completely different, so alien to the ways that we think, that even today, we don't claim to really know the final answer for what quantum mechanics is all.
No, even today, your evidence still sucks. That's what you really wanted to say, right? I mean, if you were going to be honest, that's what you'd really say. That even today, after 100 years of playing with this nonsense, we still have to resort to 2-slit experiments to give you any reason to believe. And we can only do that when we lie about how they're conducted.
About. So that's why we need to break up the discussion into sort of the accepted parts, the used way that we approach quantum mechanics, and then the deeper parts that are still controversial. We don't actually know.
No, they're controversial because the evidence sucks. Your evidence for your spooky action crapola is terrible evidence.
Many answers to questions that are very easy to ask about quantum mechanics. So that's why it's so important. Quantum mechanics is simultaneously absolutely central to all of modern physics.
And it's really not central to anything. It's just central to the people who make a living at it. And otherwise, it's completely non-essential. We landed on the moon without any of it. Did lots of things without any of it. Without any of your modern physics being necessary.
And yet, something that we don't claim to understand. So to get there, the way I like to do it is to actually imagine a fake history, physics that didn't actually happen. So this would be if quantum mechanics hadn't come along.
Yeah, that's right. If quantum mechanics hadn't come along, we'd have to have real causes to effects, and you'd have to get to the real causes of those effects, and you'd have to discover what's really happening, instead of pretending things are not where they are. This chalk isn't where it is. It's a superposition of a bunch of places. And it's deciding whether it should just hop to the moon for no good reason.
Where were we going? What is the sort of idea of what physics is that people might very reasonably have had near the end of the 19th century, beginning of the 20th century?
There you go. So yeah, at that point, we already knew we had some little bits. We had that we call matter, and then we had some other stuff called forces. So we had those 2 categories. And that was a really good place to be. And if they would have just stayed in that place and understood the 2 things are different, and they're different in these fundamental ways. The little force bits goes the speed of light. The matter stuff goes some speed slower than that. It has to be pushed along by the forces. And it takes a while for the forces to force it. You can't force it instantly. It has to push on it for a bit.
But things didn't work out that way because quantum mechanics got in the way.
That's right.
The thing that we would have thought, classical physics, right? And again,
so call this classical is just so stupid. I mean, well-established, you could say. Well-established physics, the inverse square law, the speed of force, well-established stuff through lots and lots of experiments. But instead they use this stupid term, classical physics, as if classical physics meant whatever they believed 300 years ago, when most of them believed in some sort of wave theory, right? I would argue that's, to me, hardly classical. That's your modern nonsense. It's not well established. Certainly wasn't well established then. It's not well established now.
Again, as I've said before, we usually illustrate classical physics with particles, doing things with positions and velocities, but it works equally well for things like the electromagnetic field in the middle of...
So again, this idea, this magical field made of nothing. So again, there's two ways to look at it. You could say the field is something, and you could say, well, look, what do we know? We know that gravity and light and the magnetic field all move at the same speed. And we know that it's forces, basically. So light's basically a force. And so it's the speed of force. And we know that light is distinctive because it's at a frequency, so that's a giveaway. And the rest is just gravity and magnetism, and that's just about repulsion and attraction. So the trick is what particle theory can explain what repulsion would be. And I guess the obvious one would be, that you have two objects like ping pong paddles and you have something bouncing between them. Well, that'll certainly create repulsion, right? So the closer I bring them, the more repulsive they're going to become, because there'll be more, the thing will bounce back and forth faster and faster and faster. So if we just understand the forces are indestructible, that they're energy, and that it's indestructible, that it always has a path, it's always going somewhere, the energy, it never dies anywhere. It can only be stored or trapped, and then it can be released again. So if you understand that, then all you got is this attraction thing. What could possibly affect attraction? Well, then you could understand that, well, attraction could be the fact that there's a force on the outside pushing everything together. The default force would also create attraction. As long as something ain't trapped between here, then this outside force will force these two objects into each other. So I already have attraction there, and I have repulsion here. And yeah, you got to modify them to create the right amounts of them to create something like a magnet. But you can understand the magnet, it can't be just, it's not generating energy. We know that energy has to come in before energy can come out. So it's going to do something energetic. If the magnet's going to move from here to here, that something has to be compelling it to move. It doesn't just say, I want to move. I'll just get, I'll just grow some feet and some swimming fins, and I'll just walk and swim over here. It can't do that. It didn't eat a peanut butter and jelly sandwich to get a bunch of energy, so now I can walk somewhere. So, this isn't, this is hardly brain surgery, right? I mean, the basic mechanics. And they turned it into this bizarre, incredibly strange story of enchanted beasts and quantum this and 400 little gremlin particles.
In the 1800s, Maxwell and Faraday and others worked out the theory of electromagnetism, which is a field theory.
So it's not a field theory, it's a radiation theory. So again, this is just more of the distortions that need to be pointed out. What Maxwell and Faraday demonstrated was that charges radiate. That an electron is radiating a force, and that the force has to reach another electron before the other electron can know of its existence. The force goes there by the speed of light. They communicate with each other at the speed of light, and that the force behaves in every way like it was a light bulb, and that there's just this trick to it, that I can turn the light bulb onto an opposite. So for a proton, the field is opposite. Okay, it can't be thought of as a flow, like, it flies out of the proton and goes into the electron, right? So they draw these idiotic arrows. It doesn't have a flow because obviously two protons can repel each other, and they can't repel each other if they're both, what's the way I want to put it, two electrons, which one you point the arrow going into, right? We know the into arrows isn't going to work because we know that they wouldn't be attracted. Two protons aren't going to attract each other, so I can't have both in arrows. I can't have them both being vacuum cleaners because they'll suck right into each other. And we know that doesn't happen. So we know that theory isn't true, that there isn't force going one way and force going another way out and one force goes back in. We know that can't work. So why are they pretending that's an answer when it's not an answer? So there's obviously a catch. And I can give you the catch. The catch is there's two different forces. There's blue force, and you could say red force or black and white force. It doesn't really matter. But the fact is that they just have an inverse property. So when an electron force hits a proton, it leaves sideways. When an electron hits an electron force, then it reflects perfectly. So it's just a matter of deflecting the energy into another dimension. So in one case, the energy goes out another dimension. And in one case, it either in and out or that way. And in the other case, it just reflects. And then you can explain repulsion and attraction with a mechanical theory, physical theory.
Fit into Newton's idea of absolute space and time. Electromagnetism was the inspiration for Einstein and others to invent special relativity. But the basic paradigm of things with positions or configurations and also with momenta that you could solve equations for and predict the future deterministically, the clockwork universe, all of that was perfectly compatible with everything that electromagnetism said. Even statistical mechanics, which came along at the same time in the 1870s, again, Maxwell, but also people like Boltzmann and Thomson and Gibbs and so forth, it was a slightly different paradigm because...
Well, I mean, it's consistent, but it's not consistent with this idea of a field that always exists, okay, in a sense. A field you have to augment with real changes, and the real changes happen from sources. And the modern quantum mechanics is ignoring the sources and just pretending the field was created by magic, when we know it's created by sources. The light comes from a source. It doesn't just exist in the field. It exists in the field because it was put there by a source.
Statistical mechanics, you imagine you don't know for sure what the positions and velocities of everything are, but you still think that there are such things as positions and velocities. So it was still basically the classical paradigm. So that's the direction in which people were going. And they thought that you could say that matter in the universe, the stuff of which we're made, was made of particles. So
again, this word, particle, you could just say clumps would be safer, right? Just to say it's clumpy would be a much safer bet, because you could know that the particle could just be something that was made out of something else. So you're really searching for the idea that what they were looking for was more elements, something that was elemental. That is, you couldn't divide it, you couldn't break it into any pieces and say it's made out of these different components. And that's what they were really seeking. And by the 1900s, they were already getting there, in the sense that they understood an electron and a proton. And even if these aren't composite particles, even if these aren't elemental particles, they're so close to it, it doesn't matter, because their bits don't exist in reality. They don't exist freely. They only exist in this form. You'll never find a quark all by itself saying, I'm a quark. So even if a proton is made out of quarks, it doesn't matter, because the quarks never exist as quarks. They don't exist as free quarks. So it's an irrelevant point. So you found the elemental bits. They're responsible for the most fundamental thing that's happening, which is charge. That charge duplicates pretty almost exactly magnetism. And that it's creating repulsion and attraction. So why wouldn't you figure that ultimately charge is the mechanism that's forcing electrons and protons to move, not gravity? That gravity must have charge in it, some form of it. And there, you got it. You got everything right there. You don't need anything more.
Had, by the end of the 1800s, we already knew about the electron. We were soon going to figure out something called the Rutherford Atom, which we'll get to in a second. We didn't know about protons and neutrons yet, but those were coming very soon. But we knew about atoms, and atoms had been thought of as particles in some way. So the point of a particle is, this is going to seem like a little bit too much detail.
Yeah, well, just atoms, though, doesn't give you all these other phenomena like charge and magnetism and all this kind of stuff. So it's not a good enough explanation just to say we have atoms. You really need the electron and proton to get the whole charge thing, the electricity thing, that's the real deal. So until you had that, you didn't have much.
But it'll be useful later. If this is space, a particle is something that has a location. There it is, x. I'm going to put a little vector sign because it's in three-dimensional space. At any one moment in time, a particle is here. It is not anywhere else.
Right, and whatever you're calling a particle has properties, and that's really what we're saying. What are the elemental properties? Okay, so I'll tell you it's 2 + 2 physics, so there aren't too many elemental properties. So all you really have is this idea of a charge. But the idea is you have force that equals the speed of light, it equals energy, it equals indestructible. And that we know exists. So there's something moving the speed of light. And the interactions can be understood. You can understand the actions as being clumps, quanta. That's quantum mechanics. So you could even say, proportional to. And then you got matter. And what is matter? Matter is electrons and protons. And so they have this inverse relationship. You can call it plus and minus, or you can call it minus and plus. It really doesn't matter too much how you identify it. But the fact is that there's something about this force that when it communicates between these things, there's two kinds of it. There's two ways it can communicate. And so all you really need is to say, okay, there's force that's electron force, and there's force that's proton force, okay, and it's an equal 50-50 amount of it in the universe. And it just has this inverse relationship. So if I make a magnet, I can have the two forces come in mixed. I don't know how to simply draw the other force, just dotted lines. So, I mean, if I did it in red and blue, you can understand. Red and blue comes in, and the fact is, it can be mixed. Purple's coming in, and the magnet will sit there and send all the blue stuff out this end, the electron pushing away force, and the proton pushing away force will come out this end. And the only reason why a magnet doesn't push away an electron, unless it's moving or some other kind of garbage, is merely because the magnet itself is subject to becoming charged. And if you charge the magnet, it's no longer a magnet. You're clogging the filter. But the filter is basically saying, okay, send both electron and proton force into me, and I will. I'll take all the electron force and shove it out one end, and I'll take all the proton force and shove it out the other end. And with that simple description of the reality, you've got all the basic mechanisms here. Now we don't need any woo particles. We don't need anything that doesn't know where it is in space or any of that crap. We have electrons and protons. They have a standard magnetic configuration inside an atom. With the neutrons that have an electron in them that's bound in a nucleus, and there's free electrons that have positions that are magnetically sensitive. They're not orbiting. They're just establishing distances from each other, and they end up in standard orbits, because guess what? If I add another electron, there's a standard distance it's going to be from the other electrons. And so, yes, you have orbits that are standard because the distance that magnets would be from each other would also be standard. So there, you got it. You don't have to make it complicated. So yes, you have space and real things with real properties in the space. And there's two things in the space. There's this object, this thing, a particle, whether it's a Volkswagen or whatever, and then there's the forces that are going to act on it. Period. That's all there are. Stuff moving the speed of light, force. Stuff not moving the speed of light that's moved by the force. That description of reality works.
And along with the matter equaling particles, again, physics that didn't happen, you had the idea that forces were given by fields.
Right,
we already, of course, had seen the gravitation.
No point in having the field. The force can exist without a field. It doesn't need a field. The force has quanta of energy. It has momentum. It transfers the momentum. And there's every indication that it can transfer the momentum in a dead straight line, like a photon. A little piece of momentum can go from point A to point B. That's what there's every indication of, that it's rays of force. That a force can just move through the empty space. Doesn't need to have a field.
Gravitational field. Laplace had figured out that you could do Newtonian gravity in terms of a gravitational potential field. Faraday and Maxwell and so forth showed that electromagnetism fit into the same paradigm.
And Lesage pointed out that you can do gravity with a pressure mechanism coming from the outside. And yes, it had a couple of flaws, but the flaws were based on the fact that Lesage didn't know what charge was. So he didn't know that charge is really what's moving stuff on the nuclear level. Electrons aren't affected by gravity, because they're already being affected by charge, and charge is gravity, in a sense, to an electron. An electron only cares about the force that it's going to hit it and move it. It doesn't care about the one it's going to deflect.
Unlike a particle, a field is sort of the converse of that. Fields are everywhere. So sort of, if this is space, the field exists at every point in space, okay? In particular, at every point in space, the field has a certain value. And what...
All right, so this isn't, so he's doing the classic view, but he's saying, I'm going to do the classic view in the quantum mechanical way, okay, which is I'm going to project an imaginary amount of something to already exist when we know we don't have to do that. The cosmic background radiation is a perfect example of radiation that's coming from the outside in, from all locations, and it's real stuff. It's not nothing. It's not a field. It's either it has a bit or it doesn't have a bit. There either is a photon or there's no photon. Where there's no photon, that's nothing. Where there is a photon, that's a something. And the field can have, the field around something can either be, well, you turn this light off. There's nothing happening there. So there's a nothing space. And then there's a something here. And then just like a photon, you can understand, well, yeah, it's little bits of this stuff with a nothing between them. This is nothing. There's nothing here. There's nothing here. That's what's defining the properties of the something, is the fact that there's nothing between them. And there's a certain regular frequency. You don't need any of this field stuff. The field is the energy. If there's no energy in the field, that's what the field is, no energy. If there are things in the field, then there's things in the field. But there's no field waving. There's no like corn blowing in the wind. There either is corn or there's no corn.
What matters for the field is not where it is, because it's everywhere. What matters is what the value is and how the value changes from place to place. So at each point in...
So we know that the value changes from place to place by these straight line momentum vector rules. That's it screams it everywhere. Like I said, every day you sit here and I got these light rays getting to me. We know that they're rays. I can make a little hole and the light rays will still get to me through the little hole, and the ones that don't, it's not a wave.
Space, like that point right there, you might have, for example, an electric field, which is itself a vector, and it's located at that point in space at that moment in time. So you have particles with locations, you have fields that are spread all over, and roughly the picture that was arising was particles move around being pushed by the forces.
There you go. That's it. Yes, that's valid. That's the road we were on, and you took us off that road to go to right down wooey, religious, silly, fucktarded nonsense road. Forces and matter. That's all there are. There's stuff moving the speed of light, and the other stuff is dead quiet unless you push it with something. Period. The force has to force it.
Generated by the fields. So, for example, if you have a proton, which is a positively charged particle, you have an electron, which is a negatively charged particle, there's some pull between them, which is a force due to electromagnetic.
Right. So right there, you're off the wagon. This pull thing. There's no evidence, right, of pulls, and any common evidence of a pull. Everything we call a pull, you have to push on something. Even if you're having like a tug of war, okay, and these guys are pulling this way and these guys are pulling this way. Well, they're not really pulling, right? They're not pulling this guy. They're pushing on a rope. They're actually pushing this way on the fibers of the rope. They're pushing the rope that way, right? So they're not pulling on anything, they're pushing. You open a door, you grab the doorknob, you're pushing on the back of the knob, right? You reach, you push the door open. You don't pull it open. You push the knob here. There's no pressure on the doorknob this way. Well, they're saying there's certainly no pressure on it this way. You don't, pull it anywhere. You push it somewhere. So right there, that's like a fundamental physics concept. They never talk about it, never even acknowledge it. He writes the word pull because it looks like, wow, the electrons are pulling. A proton and an electron are pulling. And what you could understand is, there's a certain amount of push. And what you've done is you've somehow eliminated the pressure between them. So now they're getting pushed from the outside, and there's nothing on the inside to stop it. Because of what I'm pointing out is the obvious way you could understand it is because the force is leaving. The force between is leaving. That means it can't go back and forth. That means it can't create a reflection. It can't stay alive. It just all leaks out. You end up with a vacuum, and the things will move into the vacuum. Simple solutions, simple answers work, and instead they jumped right over that to jump into a bunch of woo physics.
magnetism, they pull together. They also pull together due to gravity, whereas if you have an electron and another electron, electromagnetism pushes them apart, gravity pulls them together.
So again, it's all one force, and it's just the idea that the force is made of two components, the electron force, the proton force, and they have some distinction that electrons and protons can tell the difference, and they behave two different ways depending on what force hits them, and that's all there is.
And so you had this complicated but really very rich picture where particles interacted through different forces, which could compete in different ways, and therefore give rise to all the complexity of life around us.
Right, so you don't need to have a whole bunch of complex forces. All you need is 1, 2, that's it. 2 plus 2 plus 2 physics. 2 kinds of force, 2 kinds of matter, 2 kinds of interactions, and you're all done. You can explain all the complexity we see. So you don't need complexity in to get complexity out. You need something simple in, and the complexity evolves out of it. And that's the simple answer.
Pretty darn good picture. And furthermore, there was some unification of known ideas within this picture. So let's say you...
So this unifies all of them. Okay, so you get your electricity and your magnetism, you get your pushes and your pulls as visual objects. You get all of it. So it explains everything. It unifies everything into simply understanding there's stuff called force and there's stuff called matter, and the force always is moving and it never goes away. The little bits that are the field, okay, those little bits always have to be accounted for. They never destroy the energy of them, and as they bounce around and hit the material objects of the electron and proton, they change what position they're going to be in. There, that's all you need. Everything can be explained with all that. That's all you need. Okay, that's it.
Have an electron. An electron has an electric field. The electric field goes around and actually points toward the electron.
So that's more nonsense, right? We know it can't point towards the electron, because then 2 electrons would end up driving right into each other. So it's a stupid drawing. There is no field pointing to the electron. That can't be the right answer. It's, all you have to do is draw another electron next to it, and you'll see, that's not going to work.
It's negatively charged. If it were a proton, a positively charged proton, the electric field would go out. Electron, it goes in.
Right, and it doesn't work, right? I'm just saying, it obviously doesn't work. It can't be that way. And there's also no evidence that it does that, okay, that any of this in and out stuff happens. It either excretes something like a light bulb, or it doesn't excrete something like a light bulb, okay? That's it. It's either on or it's off. That's it. There's no other choice.
You can take that electron and you can move it, right? Well, imagine that you do move it. Imagine you shake the electron up and down.
Yes, and imagine I shake it. So then again, so they're giving something properties it can't possibly have, right? So they're basically saying electrons shake, okay? They can't just shake. It's like their light bending thing. It can't bend unless something's acting on it, all right? Well, an electron can't just shake. It can't just go here and then go here and do that, because it has some kind of energy. It can only do that because the field is shaking. So the field has to shake first. The electron can never be the first cause. The electron has no first cause ability. It only does what the field tells it to do. It only goes where the field pushes it, frankly. That's it. It is pushed to a new location. Pushed. It's always pushed somewhere. It never goes anywhere because it wants to.
So the electric field here is the electric field surrounding the electron. If you shake the electric field wants to be pointing toward it. But if you move it, it takes time for the electric field to realize, oh, the electron has moved, I should shift where I'm pointing toward.
Right, well, it doesn't take very long, because obviously the electron, so, this is all little stuff that, they say this stuff and it just doesn't say much, right? The field is obviously much more reactive than the electron, so the real point isn't that the electron moved and the field can't catch up. Like the electron moved to here, and the field couldn't catch up to the fact that the field is moving the speed of light, okay? The field is moving really fast. So moving the electron didn't fool the field. The field had to move the electron to the position, okay? So it's perfectly caught up in that sense. And the point is the electron took time to move here. So it wasn't that the the field is now changed because the electron's in a new location. No, the point is the field changed to move the electron in the first place, and it took it time to get to the new location, and that's what means that, well, when the electron's here, it's radiating a certain thing. When it's here, it's radiating a certain thing. So something over here. Something over here won't know about, it'll know about this later than it's going to know about this. And that's all it has to do with, is how long it takes for the information to get someplace else, because it's going to take time for it to establish this as its new position. It'll look like it's in two positions at once, you could say, if you looked at it over too long a period of time. I mean, if you took this time and broke it into pieces, yeah, okay, it could look like it's in each one of these locations, but the truth was it's moving to a new location. It's not just being in a new location, and it took time for the field to catch up. No, it took time for the electron to get there.
Okay? In Newtonian gravity, if you move a planet, the gravitational field changes instantaneously all throughout the universe. But Maxwell...
Okay, so that's not Newton either. So that's just cheating Newton. Newton didn't speculate on the speed, and he certainly wasn't certain of any speed. So he didn't make those assumptions. So he's saying that Newton assumed it, or that Newton had any evidence of it, or Newton asserted that it was instantaneous. He didn't. And certainly later in his life there was lots of conversation about the speed of gravity and the speed of light. So it's just wrong to say Newton theorized and had some reason to believe it was instantaneous. He didn't have reason to believe it first, and I don't think he asserted it. So I don't think on either one of those scores you have any evidence that Newton said, yes, it must be an instantaneous force. He didn't say that.
And others showed that this change in the electric field, and likewise a change in the magnetic field, does not happen instantaneously throughout the universe. It propagates outward at the speed of light.
The speed of force, right? So this is a key place where, like plus and minus, and the fact that they did label those things wrong. He didn't point out how, well, they do have those labels backwards. The electrons create the positive, the excessive condition. They're the aggressive thing. They're on the outside of the atom, and they're the thing that is creating the effect. And you can have too many of them or too few of them, and so they're the thing, that should be labeled positive. So he doesn't point out how they got that wrong, and they never fixed it. Okay, but getting back to, what the hell was he talking about? The speed of force, rather than calling it the speed of light. If they had called it the speed of force, then I think people would understand that light's just under variety of the same thing that the other stuff is. But by calling it the speed of light, they're weakening the meaning of the forces, and now they're just saying the forces move at the speed of light. No, the forces move at the speed of force, and light happens to be one of the forces. Light is the little stuff pushing things. Light isn't one of the things that's pushed. I mean, a really rudimentary and foundational kind of mistake. And I would call it a mistake. I don't think there's any good reason for them to say speed of light rather than speed of force. Maxwell discovered the speed of force, not the speed of light.
And that's because if you take this electron and shake it up and down multiple times, the electromagnetic field vibrates, it pulsates, and the disturbance that you have created in that field propagates outward in the form of a wave, and it moves at the speed of light because that...
All right, so none of that has to be the explanation. The evidence is I just drew it here. When something's moving, okay, and it's reflecting force the whole time it exists. So while everything exists in the universe, there's constantly stuff bouncing off of it. Constantly it's showing what it is because the energy hits it and reflects off of it. Right? So the basic idea is stuff goes in and stuff, and even if it's coming out perpendicular, right? So let's say this was a blue arrow and it went in here and it comes out perpendicular. Well, it's still radiating, and when there's nothing else in the universe, you won't be able to tell that that was a perpendicular reflection versus a regular reflection. But you'll have just as many pieces coming in this way and reflecting back out that way. So you'll never be able to tell. But that's what it's really doing. And so if I move something from this position to over here, obviously, okay, if I'm sending energy to it that's going to reflect, right, I'm going to get that reflection back, and it's going to reflect back. And so I'm communicating with it essentially at the speed of light. So anytime I move, this thing is going to be affected by the movement because I'm either going to be hitting it more or I'm going to be hitting it with less information. right? So there's either going to be more little arrows hitting it from me or less arrows hitting it from me, which means that its stability, its position will have to change. Because I change this position, I'm going to change this position. And that's how things are communicating. They're not waving at each other. Okay, they're sending messengers to each other in the form of quanta of energy. Little bits of energy moving the speed of light. Little particles. Perfectly valid theory that works, it explains, and they gave up on it. They just decided they want to go with a woo.
That's what light is. Light, as Maxwell showed, is a wave of...
No, it's a force. Okay, and like all the other force bits, it's just made out of the blue and the red stuff moving the speed of light. And that's it. Light's just force, and it's force at a frequency. It's bullets fired at a frequency. And so we can detect the frequency that the bullets are fired.
Electromagnetism. So the electric and the magnetic fields vibrate, and we see that as light of different wavelengths, of different...
So it just magically vibrates this field. It's magically vibrating all over the place when obviously it's a straight line force in every other experiment. So again, there's no reason to believe their theory. There's every reason to believe that this works, and it's really simple.
Colors, for example. So that's nice. You can see how, something that you didn't know, whether it was a particle or a wave, namely light, you say, now we know what it is. It's a wave. Newton thought that...
So, no, it isn't. So, it's just a stupid conclusion, and you'd have to be way jumping the evidence to assert it with any kind of authority. Especially when you know particles can behave like waves.
Light were particles. Light were what he called corpuscles. He had evidence for it. He said when you have your hand near the ground, it had cast a shadow with sharp edges. The light doesn't go around like waves do. But it turns out that's just because the wavelength of light is very, very short.
Oh, no. Well, that's just an excuse, because we know that it doesn't matter how short the wavelengths are. It has to do with the tension in the medium. So if the medium likes to stick to itself, then it's going to try to stick to itself after it goes through a small impediment. And the smaller the impediment, the more likely it is to go right around it. So again, that theory is nonsense. It doesn't have anything to do with the frequency. It has to do with the fact that it has to be something syrupy. It has to be something, there has to be tension between the force bits. And there's no evidence there's any tension between forces. Forces don't interact with forces. You can shoot light bulbs at each other all day long, and you won't see the photons bouncing off of each other. So it's just wrong.
So light is a wave in this field. Electrons, which are particles, created. It's a very nice picture that is coming together.
No, it's a garbage picture, and you've straw-manned Newton with stuff he didn't say, and in a sense, you should straw-man, Maxwell, because again, those are just assertions by Maxwell. That's not proven by any of the mathematics. The mathematics, when he draws it, will be straight line force. When he draws a charge and how it's affecting something, he's drawing lines of force, straight lines moving out of the object. The field lines are just representations of a measurement of the strength of the force. They're not real lines.
Sadly, around the year 1900, not so sadly, but remarkably, around the year 1900, this picture begins to fall apart, and it falls apart in two different ways.
So yes, that's the wrong description of where they were headed. So where they were headed was this, and they fell off the wagon with Maxwell. Maxwell was that was a critical error, was to deify Maxwell's rhetoric. His math was okay, but the stuff he superimposed on the math, anyway, any notion of a wave, there's no waves in his math. It can all be explained by vectors, straight line vectors. It's vector math, for fuck's sake.
Falling apart, this picture. And how can it possibly fall apart? Well, we could question classical physics, but we're not going to do that yet. We could question the particle nature of matter or the field-like nature of forces. And
right, well, I certainly would question the word field tied to force. Force doesn't create a field unless you send it that way. So I can send soldiers that look like waves, but that doesn't mean anything. The soldiers aren't tied to each other. They're not obligated to be waves in any way. They're just obligated to be something that marches towards the enemy and stabs them individually. They do individual work. They don't do collective work.
Light. So it turns out we did both. We showed that light has particle-like properties. This is very vague sounding, but that's important that it's vague sounding because...
No, it's not important. It's evidence of, again, the fact that you're not very good at doing this idea of scrutinizing the evidence, because you want to scrutinize it. This saying it has particle-like properties is so vague and indescript and meaningless. What's going to be your argument? Well, yeah, it has a lot of them. It behaves as if it's moving in a straight line and that it has a clumpiness to it. Those are facts. So it's clumps moving in straight line vectors. Well, it certainly has those properties.
When we came up with the idea, we didn't have a full theory. It wasn't like you went from classical physics, boom, to quantum mechanics. We sort of clawed our way up very gradually, and so we made all these vague sounding statements before the whole thing finally clicks together.
And it doesn't click together, so let's understand it doesn't click together. You can't imagine it as a coherent theory. It's still got wooey crap in it, a virtual photon, because they can't account for the things that's happening, so they call it a virtual photon. And what the hell is that?
So what does this mean? This is the phenomenon of blackbody radiation. And the people who figured it out were Max Planck. I'm very inconsistent about whether I pronounce German and generally foreign names correctly or not, but it's Planck. If you were Mr. Planck, Professor Planck, that's how he would pronounce it. And of course Einstein also came along to clean things up, as he so often did. So the point...
Yeah, there's not much of a point here, right, except for the silly expectation that there was somehow infinite energy. You could make an infinite photon or something, an infinite frequency of a photon. And they figured out, well, no, there's no infinite frequency, so there has to be a limit. You can't make a 5 million gazillion gigahertz frequency. You can't put quanta. You can only put them so close to each other and no closer, kind of thing.
Is that a black body is just something with a temperature, okay? When you look at things in the world, you see they have colors and textures and all that stuff, but you're seeing light reflecting off of it. There's also the glow that the objects give off intrinsically. Usually you don't see that because room temperature objects glow in the infrared and your eyes are not attuned to the infrared. But if you heat something up so that it glows in the visible light, then you can see it glowing, and that's blackbody radiation. And the nice thing is, it doesn't matter what the thing is made of. Blackbody radiation is exactly the same for everything.
Hold on a second. Alright, should be back. Alright, so this Planck thing, I mean, there's lots of ways you could illustrate these limitations that we should have figured there was a limitation, right? I mean, you can't get infinite energy into a system, so even though it gets proportionally stronger and stronger, you can understand there's a limit to how strong it could get. So depending on how big you make a quanta of energy, let's just say, I mean, obviously I could have a photon with this much separation. But there's a point where I just run out of space, right? I mean, I can put them right next to each other, but I can understand that this stream is still moving the same speed of light that this stream is moving. And clearly this would have more energy in the sense it's got more mass, but I can't increase the mass exponentially. I can't just keep going higher and higher and higher. I can't get any more energy out of this system. Once I put these things right next to each other, that's all I got. I can't put them on top of each other. And even if I could, okay, well then, yeah, they could say, yeah, I could just make an infinite number of them right here on top of each other and get infinite energy. Well, obviously the point is that, yeah, this is what they figured out. Oh, okay, the clumps can only be so many clumps, and then you can't make the clumps any closer. You've gotten all the energy you can get out of one ray of this stuff called energy. This ray of energy has a limitation. This is as much as you can get out of a certain amount of time at the speed of light. Unless I change some physical fact, I make something impossible possible, like they can be on top of each other, I can't provide you any more energy in a ray. I can make more rays, but I can't make a ray have any more energy. So that's the limit. Not exactly a earth-shattering observation. Not something they should have thought. Again, the very fact that they weren't thinking about any of this stuff in these kind of rational terms, that they would be surprised that there was a limit to how much energy you get out of a ray that's at a frequency. Well, all you have to do is do this and say, well, I make the frequency smaller and smaller and smaller. Oh, look, my two fingers hit each other. I guess I'm out of frequency, aren't I? Yeah, all out. that you run out of frequency. That's all this is saying. And they think this is earth-shattering discovery.
The problem was, if you took this paradigm, matter is particles, so there's all these vibrating atoms in the object you're heating up, forces are fields, so light is a wave of electromagnetism, you could calculate how much energy should come out.
Right, so you could calculate. So yes, your calculation doesn't know that the pieces can't pile on top of each other. So until you tell your math that these quanta have a size, and the size won't allow them to be any closer together, yes, your math is going to be stupid and do stupid things. So yes, they calculate something that's impossible because they're not giving anything a real dimension. Their math is superficial. It's a generalization. It's not specific enough. Their math is ignorant. Okay, and so until their math is incomplete would be the simple argument. They have a mathematical formula that started off incomplete. It didn't realize these clumps have a size, and their size means it can't have an infinite frequency.
In the form of blackbody radiation, and furthermore, you can calculate at what colors it comes out, right? We know that long wavelength light is toward the red end of the spectrum, short wavelength light is toward the blue end of the spectrum, and we have ultraviolet, which is even bluer than blue, very short wavelengths, invisible, and we have infrared, longer than red, even lower wavelengths, longer wavelengths, lower frequencies. So it turns out that there was what is called an ultraviolet catastrophe. It was only called that later, but that's okay.
Right. It wasn't really have anything to do with ultraviolet or any catastrophe. It just has to do with the fact that there should, by their assumptions about how these things are even made, that they make these assumptions that they're all equally easy to make. That somehow atoms can produce X-rays just as easily as they could produce infrared frequencies. And the more sensible argument is to understand that it's harder for the system. The system needs more energy in to create their X-ray out. And there's no source of the more energy in to create the X-ray out.
I think Paul Ehrenfest called it that. The classical theory of blackbody radiation predicts that there should be an infinite amount of energy being given off at very, very short wavelengths from a blackbody. That is clearly false. It is clearly not what actually happens. And so it was Planck who came along.
And why is it false? It's false because there's no infinite frequency. That's why it's false. You can't make billiard balls line up on top of each other.
And said, you know what, I'm just going to guess. I'm not exactly sure what his thought process was, but his guess was, rather than being emitted in smooth, continuous waves, the kinds of light that was given off by a blackbody came in discrete chunks. There was a certain amount of energy given off one at a time. It was not smooth and continuous. It was quantized in some sense. Okay, this is the beginning of quantum mechanics, circa.
Right. So this could be deduced to, again, if they had gone with a magnetic understanding of atoms. You can do this simple figuring that if the electrons repel each other and they're magnetic, you could understand that these electrons would repel each other this way and they would be attracted to the proton, and that this would be an equalizing tension, that they'd have a will to move in, but they can't because they have to get closer to the other electrons to move in. So they were all in tension and they would just stay in those positions. And you could understand that if I was going to add another electrons, that I could add them in these locations because they'd have the same tension, the same attraction, and that they'd all be a different tension though. These ones in the inside would be under more pressure than these ones on the outside, which would be looser pressure, and then these would be even looser pressure, and that would be how it would work. And they have it backwards in the sense that they think this is the low pressure electron and this is a high pressure electron. So they even have that inverted. Not that it matters much, but the truth is that it's not jumping in, it's jumping out. You're gaining, you're releasing energy when you take something on the inside and you move it to the outside. You're releasing energy. You're absorbing energy when you push something from the inside and you push it on the to the inside, right? That makes sense, right? You hit something from the outside, you're giving it energy, you're pushing it closer to the proton, it locks into a position. You can sort of understand that now you have potential energy. You don't have kinetic energy, you have potential energy. The energy is caught between the electrons, and until you pull the electron out or push it out, you're not going to release the energy until you make the electron move.
1900, when Planck first made his suggestion. And his suggestion was that light comes in chunks of energy, and the energy depended on the frequency of the light. E, the energy of each little chunk of light, was a new constant of nature called h times the frequency. H is cleverly now called Planck's constant.
Right. So this was just making superficial assumptions that the energy of a quanta is somehow its frequency. No, the energy is in the momentum of the little bit. And they're just bullets. All the bullets are the same. The bullets in ultraviolet light are the same as the bullets in infrared light. And the only difference is they're closer together, so that way you can hit something with more of them in less time. And timing is everything. So if you want to tip a pole over, you have to hit it constructively. So if you add a bullet, you have to add another bullet while it's still moving in the right direction. If you add the bullet when it's moving in the wrong direction, you're not going to tip it over. You have to tip it over by keep adding the energy in the right direction, the same direction that the thing is moving. You got to add the energy in that direction. If you add it the other way, you're not going to knock it over. So there's certain rules to this tension argument and getting things out of their tension. You have to hit them a certain way to get them out of their tension. So that's the logical argument here is the high frequency will do it because it hits the electron before it can get back to its normal position. It hits it while it's still moving in the right direction, or before it's gotten too far back. You can make it go forward. You know, it goes this way and then it comes back a little, and then you hit it forward again. You can get further than if you wait for it to all the way get back, right? So low frequency light allows the electron to go back to its normal position. High frequency light pushes the electron further out of its position. It's that simple an argument. That explains all of this crap, and you don't have to sit there and make this silly argument that somehow frequency is energy. Frequency can be energy if we're going to define energy as how far did I move the electron in total distance. But it doesn't, because that's just a timed argument. It's not more absolute energy. It's only more energy in a specific amount of time.
And it joins things like the speed of light and Newton's constant of gravity as a fundamental feature of the natural world, a fundamental parameter of physics. I will tell you a little secret, not much of a secret, but a little trick.
So again, these are all just the mistakes in reasoning that just keep putting bad facts in the mixing bowl. So they just keep now throwing all these, you know, they had some pretty good facts with Newton, and those people, they learned some things. They didn't jump the evidence. They didn't go too far. They didn't say too much. So they kept the fact bowl pretty clean. And now they're just throwing the woo in, throwing these little wooey facts in that aren't real facts. They're half-truths. And half-truths are very dangerous.
Usually in physics, we define the angular frequency omega. So f, the frequency, is literally how often things go up and down. You multiply by 2 pi to turn that into an angular frequency.
Right. So this whole notion that somehow the electron isn't going this way, it's going this way and all this other ways, and absolutely no reason to think real physical objects do that. They only travel one way at a time. That's it. They can only move a total way. They always add the forces. So automatic in whatever these little particles do is the rule that they can't go two ways at the same time. They can't go this way and this way. They can only go that way. They can only move one straight line at a time.
So omega is 2 pi times f, that's the angular frequency. And then we define h bar to be h, Planck's constant that he invented, divided by 2 pi. So E is h bar omega. And this is a very famous formula, Planck's little formula.
Yeah, it's garbage. So it's again, the frequency is just incidentally meaningful. It only means something to electrons and atoms. It doesn't mean anything to free electrons. That's certainly true. And you know, the H is just an acknowledgement that yes, there is a limited size to the quanta. It takes up a certain amount of space, and that's all it's really saying. So it's almost an irrelevant constant. You don't need it to do this. This logic that they're really saying is they're saying energy equals frequency. They're not paying any attention to this H bar.
And what Planck is saying, remember, is that black bodies are giving off light, giving off radiation, not as a smooth wave, but in chunks. He didn't quite go so far as to say that that's because light is individual particles. That was Einstein. Einstein came along and said, forget it, not just blackbody radiation, but in other contexts, in the photoelectric effect, for example, light comes out in these quanta because light really is particles. And so we now call these particles...
Right, so just point out, I mean, there's no point in pointing it out, but again, so Einstein's right about the bent space thing, and he's right about the relativity thing, but he's wrong about the quantized energy thing, or whatever. So, you know, let's understand their evidence is so weak that it didn't compel Einstein to believe, and yet people ridicule me for not believing. So somebody like Einstein wasn't compelled to believe, and Einstein believed almost anything, right? You could fool him with any kind of crap. I mean, he went for bad space, right? He fell for that. I mean, that's just too silly. So he was foolable, and he wasn't fooled, you know. And so, you know, there's good reason not to believe this crap.
Particles of light, we call them photons.
Right, so another bogus word, though. Okay, we call them that. You know, Einstein used the word, but the idea wasn't that the photon is this. Okay, photon. You know, that doesn't work. Wasn't what they didn't say. Photon equals quanta. No, the idea was that the photon was quantized. The idea is that the photon is clumpy. And all the evidence indicates that, because, you know, we have to have 6 of these little things or we don't see the photon. Frog sees only 3 of them, maybe 4. Right? So there's different rules based on the fact of how long this thing is, how big it is. So photon isn't one word. Oh, photon. No, photon can be this, or it could be twice as much as that for a human being to see the ray. So it's really just a ray-ton, okay, if you want to call it that, ray-ton, all right, and the ray-ton is a composite. It's made out, I mean, it's an emergent, so it's made out of pieces, and the pieces are clumps of energy, quanta, okay, at a specific frequency, and the quanta without a frequency is gravity, and the quanta segregated based on which one's blue and which one's red is magnetism. And there you have all you need. You have all the ingredients to make the universe right there. You don't need to go anything else.
Thing that the name nomenclature came along later. Okay, so that's interesting, but it was also disturbing because, you know, literally one of the greatest triumphs of 19th century physics had been understanding that light was a wave in the electromagnetic field.
Yeah, bullshit. So it wasn't a triumph, obviously. It was just an assertion by etherists. So let's understand Maxwell was an atheist. These people won't admit they're atheists, but, you know, and that's why they like Einstein's bent space, is because it's ethery. You know, but that's all this is. It's just ether.
Here's Einstein and Planck saying, well, it has light also has a certain particle-like kind of behavior under certain circumstances, and it involves this new constant of nature, Planck's constant, and it has sort of a quantum.
No, it has this notion that the frequency is limited, and so what's limiting the frequency? What's preventing you from having a higher frequency? Well, what's preventing is the quanta clumps are too close to each other. They can't have an infinite frequency. There's a certain limit to how many you can stack in a row, and that's it. You're all done. You've used up all the empty space between them. You don't have any more room.
Feeling. Quantum just meaning a discrete unit of something, okay? So that was in the back of everyone's mind. That is something that is going on. That was fact number 1. Light has particle-like properties. Fact number 2 that people began to discover, matter, like electrons and atoms, has wave-like properties.
So this was when they really go loop-de-doo, right? Because there's so little evidence of any of these wave-like properties. So little evidence that electrons wave their way anywhere, that they are not discrete, that they are not clumps moved to different positions in space by forces, that they don't have any waviness. They don't wave anywhere. It's just idiotic.
Or field-like properties, if you want. Where did that come from? Well, remember this picture that we had, that we were putting together of classical physics, the world that could have been, but it didn't actually happen, featured a bunch of particles interacting with forces, and they came together to make atoms. So it was the Rutherford atom, named after Ernst Rutherford, that is the famous picture you always see. So the Rutherford atom has, you know, protons and neutrons in it. There's proton, 2 neutrons, and then there are electrons circling around in orbits, circles, or...
And this just had to do with the idea that Rutherford threw atomic nuclei at a piece of gold leaf and found that some of it's deflected, which makes perfectly good sense because it's repelling when it goes towards the positive parts of the nucleus. But sometimes it plowed right in and bounced straight back, and indicating that you actually had a hit there. And so it was just kind of a cue ball kind of experiment. You know, you set up 4 cue balls and you throw one down the table and see if you can hit the other ones or something, you know. And yeah, there's mostly empty space, so you mostly hit empty space. So most of them go through, and then the ones are deflected by the field. But if you hit it head on, there's no deflection, and therefore it goes right into the nucleus and repels and bounces back. So yeah, it's a pretty good way to test So it's a pretty good theory of the atom. Now the part that's the stuff swirling around, this is because they were obsessed with gravitation and maybe electricity, and they weren't really thinking, well, why wouldn't magnets do this? If I make these all little magnetic monopoles, if I make this a little, if I make an electron a north magnetic monopole and I make the protons a positive magnetic monopole, I can create a situation where the magnets all stay in their position. I can levitate them in these positions in three-dimensional space. So if I had real three-dimensional space to work with magnets, I could put the south magnet, if I could make a south magnet, put a south magnet in the middle, and I could arrange north magnets where they're repelling each other, and the tension would keep them in one place. They don't need to spin around anything. So I can get rid of the whole gravity theory and just have a magnetic atom, and it'll work just fine.
Ellipses or whatever, it's kind of like a little solar system, okay? That's the Rutherford atom.
So it doesn't have to be. So the part that Rutherford did it was valid, okay, is to say there's empty space in the atom, okay, and it's made out of these constituent bits, the positive and the negative, so that's all good stuff. But spinning, you don't need to orbit anything.
And he got this experimentally by shooting little helium nuclei at gold foil and seeing that sometimes they recoil by a huge amount, as if the helium nuclei had hit something small and dense and hard to move, namely what we now know of as the nucleus of the atom. And this is a very successful picture. This is so successful it's used basically as the symbol for physics even today, right?
You could argue that it never really hits the nucleus, that it just repels from the force that builds up. So by my theory, the positives would be as you move the nuclei. So the nuclei it's a positive because it's a nucleus, so it's proton heavy. Okay, so you got something like a big proton. We could just call them big protons. The nucleuses. Because they're proton heavy. They have many more protons than neutrons, and even though the neutron has really got an electron in it, I won't go through all that crap. It's positive decidedly. So the point would be is that there's the proton force that's trapped between these two could never escape. It would just keep bouncing back and forth between these two, pure reflections. So you have little ping pong balls bouncing between these two paddles. And as the two paddles get closer and closer, they bounce more because they hit the surface much more, because obviously they're traveling a lot less distance and they're always moving the speed of light. So you can obviously, the pressure gets intense, almost infinite. When I get the proton really, really close, there's an insane doubling every time of this amount of pressure. Huge pressure builds up, and so it really bounces off of the pressure. It never really hits the other nucleus. The nucleus just bounces off the pressure.
The Rutherford atom, this famous picture. The problem is it can't be right. We knew instantly that this picture couldn't possibly be the right answer. Why?
We knew instantly? Oh, that's why you kept it for 50 years? Or 150 years? Jeez, amazing. We knew instantly.
Because we knew that if you take an electron and move it, it gives off electromagnetic...
Well, this whole moving the electron thing, you move it with what? It vibrates by fun. So he's saying the same thing, is that this orbit would somehow, because they were etherists, they're basically arguing that the electron's moving through a field. It's moving through some cornfield, and it's got to plow the corn as it's going. And by plowing the corn, it's irradiating all this crap every time it moves somewhere. So it can't possibly spin around here because it's moving too much corn. That doesn't make any sense as an argument, that it's going slower and slower because it's got to go through the thick field and so it crashes. Well, obviously we can imagine orbits that aren't cornfields. We can imagine that the force doesn't necessarily have to be an impediment to its progress. A mechanism. But the irony part is he's saying this is the flaw, and then he says, well, because we standardized these orbits, somehow we took away the cornfield. So there's no electrical field that now the electron can spin all it wants to here, or it can spin all it wants to here, or it can spin all it wants to here. When isn't the real logical argument that the electrons repel each other, and it's the amount of repulsion of the electrons that's deciding these orbitals, and that these orbitals are going to be related to the fact that you're getting further away from the proton, so the proton force is getting weaker, and the electron repulsion force stays the same. So the electrons are still repelling each other the same amount because they have the same distance, but the proton force is getting weaker. So the truth is that the orbit in the center is tight, and these all get like a bullseye. They get wider and wider as you go further out, would be the sensible deduction. But screw that. Sensible deductions? No, that doesn't have to be part of physics.
Radiation, that's where light comes from. Literally all the light around you right now is coming from vibrating electrons.
Says you, right? So he just asserts this stuff. A vibrating electron did it. No, the electrons have to be moved into a new position. I'll agree that the position changing of an electron is what's creating what we call a photon. But you have to move its position with something real, not something imaginary. And so photons make photons. Electrons don't magically produce them. They have to be hit with energy to give back energy, and that's the simple rules of energy. And so what you're really just doing is changing. When you change the position of an electron, you change how soon you're going to hit it. So if I'm sending light at these two electrons evenly, obviously the one in this position is going to reflect sooner than this one. Obviously. So that's going to change my world. Okay, it's going to potentially create a frequency. So if the electron moves back to this position, then there'll be nothing happening because no force can reflect while it's moving in the same direction. Say the force was moving in this direction. The electron moves in that direction. Then the force can't be reflecting off of it. But as soon as the electron stops, well, then all that force is going to reflect all at once. So you're going to have a buildup of force. So you're going to have a thickening of the amount of arrows that are reflecting because you denied them the possibility of reflecting by moving. So that's the simple explanation for what's creating the photon, is changes in the position of the electrons, and those changes are caused. They're an effect. Yeah. So, I mean, you have to have energy to make energy. You have to have a photon to make a photon. You have to move something and then move it back to create a photon. But let's understand, he'll say that, a photon wiggles an electron. Well, let's understand, the photon, the polarization of the photon is this big. The electron is that big. So how does something waving this big only affect that one electron and not affect this one, not affect that one, not affect any of these others? Just this one little tiny one right here. How does all of this get absorbed by this? That's not possible. That's not realistic. Obviously, the phenomenon is more complicated than saying the electron jiggles and that makes a photon. No, that makes one little tiny piece of the photon. A whole bunch of electrons have to jiggle. A whole bunch of electrons have to move their position, okay, before you create something that'll be a photon, this big thing. It's a group behavior.
And in this Rutherford atom, you have electrons moving in circles to beat the band. That counts as moving, okay? That counts as vibrating. These electrons should be giving off light. So if I move this over here, this is the picture that Rutherford thought was the case. But what actually should be the case is something more like...
So this is a silly idea, right? The fact that the electron is moving, it should be giving off light. There's no reason to think that unless, you believe there's some sort of ether that it's plowing through and banging into. But again, I would argue the electron isn't spinning around.
Nucleus at the center, protons and neutrons, and what the electron should be doing is spiraling into the center very, very quickly. Why? Because as the electron is moving, it should be giving off light, it should be radiating. That's a terrible looking photon I just drew there. Can't really draw from right to left very well, so I'm going to draw it this way. It's giving off photons. It's giving off light at all times. It's losing energy. It's spiraling in.
Right, so they're saying that giving off photons is losing energy, when I would argue that there's no evidence that you have to lose energy to make a photon. The energy is already in the system. It's already in your position. So whatever your position is, that's your potential, and it's all part of its potential.
To the middle. So every atom in the universe, if Rutherford's model had been correct, should be wildly unstable. How long does it take for all the electrons to fall into the center of the nucleus? About 10 to the minus 11 seconds.
Right, so this is all crap they just made up, right? Because they made this electron swim through glue. They made it run out of energy. But you didn't have to invent the glue. There's no evidence that the electron is swimming through glue.
So 1/100th of a billionth of a second. So all the matter in the universe, including you and the tables and Ernst Rutherford, etc., should be dramatically unstable. That seems to not be how things actually are.
So just look how irrational this argument is going to be. He's just debunking the fact of an orbital, and now he's going to argue for orbitals. He's going to say it's okay, though, if I put him in a special orbit, because then it's not running through the glue somehow. There's no glue at certain points. That's what he's going to essentially say. Because he's still going to have the electron orbiting the nucleus. He's just going to change the rule and say it doesn't make photons anymore.
So this was a challenge. This was a challenge to this otherwise super-duper successful way of thinking about particles and forces and so forth. What to do about it? Well, there were other clues. There were clues from how light is given off by...
Magnetize the atom, and then you fixed all these problems. No problems. Just use magnetism. Electrons are negative, north side monopoles. Protons are south pole monopoles. There, problem solved.
Gases, spectral lines, and so forth, that led Niels Bohr to suggest a modification of the Rutherford atom. Niels Bohr actually served as basically postdoctoral researcher in Rutherford's lab for a little while.
Yeah, and he was also a religious kook.
And Bohr said that you have the nucleus, just like Rutherford thought, okay? But rather than the electron being just a particle that can be anywhere, there are certain allowed orbits that the electron can be in. And other orbits are just places where the electrons are not allowed, okay? So the electron can be there, or it can be there, but it can't be in between.
Right. You can understand this. Like I said, if it was magnetism, you'd understand exactly why there would be these distances between the magnets. Because normal magnets will do that. They'll establish a comfort zone. And so obviously, if you just make this a geometric model, you could put 4 electrons in the center here, and that would fill that up. And then you could say, okay, you're in 3 dimensions. Obviously, you could put a couple more in, right? But you can put a couple this way, and this way, and this way, and this way. So you have those 6 sides of the 3 dimensions to use. But anyway, the point would be is you could understand that there'll be a certain geometry where anybody on the outside would have to go to the other edges. I drew the picture already. It's just so... It's so obvious that this should be part of the consideration of a theory. That this should have been something talked about, and there's no evidence that they even considered it, which is bizarre. So obviously you can understand if this is a positive, I could have a negative here, and I could have a negative here, and I could have a negative here, and I could have a negative here. It's just kind of obvious to say, well, where would the next negative fit? Well, obviously it would be here. And obviously this one could fit here, and this one could fit here, and this one could fit here. It's obvious that that would be the way electrons would behave. They would go to some place that's neutral, that's balanced. They seek balance between the fields. They seek a balanced position, a balanced distance from each other. That's what they're going to seek. And that you end up with a square, and then you could end up with another set of electrons at these positions. That is totally reasonable, makes perfect sense. It explains why these distances are standardized. That's why there's a standard distance. It's because of this obvious mechanical reason.
That's just the rules. Why? Because Niels Bohr said so. This is circa 1913, approximately. And, well, you might want to ask, why is that true? And Bohr's answer was he didn't know yet. He was just making a guess, like Planck made for blackbody radiation. You might also say, well, what orbits are allowed, okay? The answer is, if this distance is r, the distance from the nucleus to the electron, then the angular momentum of the electrons, turns out, if you want to fit the data, if you want to understand the light that is given off by these gases, the angular momentum, which is given by just the ordinary momentum, p, so you have some electron moving here with a velocity, and so it has p equals mv, momentum is mass times velocity. You can special relativityise all this stuff if you want, that's the Newtonian version. P times r is the angular momentum, and Bohr just says, you know what, this quantity, the angular momentum of the electrons going in its orbit, is quantized, because I said so. And what units is it quantized in? It is n, so that's just some integer, some number, 1, 2, 3, 4, etc., times h, times Planck's constant. So
right, which is insanely small. So obviously this wouldn't work rationally because we know the atom is really big in the sense that there's a lot of empty space. So there's a lot of empty space, a lot of Planckness to get rid of. So the distance between the nucleus and the electron can't be Planck's constant. That's how useless this constant is. It's got to be much, much smaller than that.
That's where you begin to think that something miraculous is happening, right? Planck came up with his constant by saying that light, which is supposed to be a wave, has particle-like properties, and you need to introduce a new constant of nature to fit the data.
See, atoms are big, okay? It's like, the wavelength of light is, in nanometers. So an atom is half of a nanometer, so that's a small amount. But you can understand that it's kind of a huge amount if you just say, well, light's only made out of 2,000 of those. The average frequency of light. It's not that many. So it's not that many orders of magnitude smaller than the frequency between light. And we know that the light quanta have to have some sort of size. Well, I'm just saying that I think it's a mistake. Obviously, constants are always suspect.
Here, Bohr is saying that electrons, completely different phenomenon, have to be quantized in a different way. Only certain orbits are allowed. But to fit his data, to fit the data that he cared about, not the data he collected, he was a theorist, but to fit the data that he knew about, the quantization condition, the chunkiness of which these electrons had to participate, was also characterized by the same number as what Planck came up with, the same constant of nature.
Right, and it doesn't explain why this electron wouldn't be plowing through the same electric field that was deteriorating its orbit and causing it to crash into the nucleus. So this doesn't solve the syrup is going to slow it down argument at all.
Constant. By the way, you might want to know, what is the number, Planck's constant? Some number of joules, seconds, whatever it is. I have no idea what it is, because every good physicist sets h bar equal to 1. Just like we set the speed of light equal to 1, and then we get on with our lives, because no one remembers how many joules or whatever per second h bar is. So we use much more sensible notation than that, and therefore, in fact...
Right, therefore, in fact, constants don't mean a damn thing, right? They just turned them into 1, so that it's all neutral in the equation. So just as I stated, the constant doesn't mean a damn thing.
It's almost impossible for me to remember where the h-bars go in almost any equation. So if I write down equations and I forget the h-bars, that's because in my brain they're set equal to 1. Okay, so that's evidence that something is going on. I mean, it seems like a little kludgy, right, a little ad hoc, and it seems like you're doing violence to the fundamental principles of classical physics, and that sounds bad. But
yes, it sounds like completely convoluted nonsense. It sounds like you just contradicted yourself. You say this solves your glue problem. It didn't solve your glue problem at all. You still aren't explaining why that special place is a special place. Why is it special? At least my theory explains why it's special. Because the charge is dictating how close and how far away the protons and the electrons are going to be. Charge is doing it.
Also seems to fit the data, and it was sort of nicely consonant with what Planck and Einstein had said, so that sounds good. But you still want to know why something like this is true. And the answer came along from a couple people. The answer is basically that, like we said up here, matter has wave-like properties. So the answer is that rather than just...
No, it doesn't, but whatever.
Thinking of the electron as a little particle moving in a circular orbit, think of matter waves.
Why? Matter waves. Why would I think about something that's just idiotic? Yeah, sorry, it's just idiotic. It doesn't wave, it moves. Period.
And the first person to say this out loud was Louis de Broglie.
Right, who came up with the notion that Volkswagens have a frequency. So you're going 50 miles an hour down the highway, you're a frequency. Even though there's no evidence you have a frequency, we're going to give you one anyway.
In his PhD thesis, so, those are the standards for the PhD thesis. You're Louis de Broglie, you say electrons are waves, not particles, okay? And what he says is, very much like what Planck said and Einstein for photons, for particles of light, he said that you can associate a wavelength with an electron. The wavelength, lambda, is the de Broglie...
Well, of course you can, because you turned energy into frequency. You did it earlier, so of course you can, because you already said E equals F. And it's not true, but you said it, so now you're stuck saying, okay, well now I can do lots of things with this E equals F bullshit.
Wavelength, and guess what? It is H.
So I'll just turn the momentum of an electron and the energy of the electron into its frequency. An arbitrary fake number I'm going to just make up based on how fast it's going. How much mass it has.
The Planck's constant divided by p, momentum. So a fast-moving particle has a short de Broglie wavelength. A slow-moving particle has a very long wavelength. Why?
Well, it's not just about how fast it's moving, right? Momentum is about mass. So clearly, the more massive you are, the more likely, even if you're going very slowly, that you have a huge frequency because you have a ton of mass. So momentum is mass. So we can't play this game that I said momentum, but I didn't include mass. Well, no, the momentum is mass. So you just said the fatter it is, the heavier it is, the more it has a frequency, the higher its frequency, which is just bullshit. Just mathematical game playing, that it doesn't have anything to do with the reality. There's no reason to believe any of that.
Is this an interesting thing to say? Well, if you go back up to Bohr's atom, to Bohr's condition, the angular momentum has to be a certain amount, and you say, well, I'm going to interpret that as saying that when the electron does an orbit, there needs to be an integer number of de Broglie wavelengths around the orbit, okay? Then you get Bohr's quantization condition. You get it. I'm not exactly sure. I'm looking at my notes here. I didn't actually write down these equations, so I might get 2 pi's in the wrong place. Sorry about that. But the point is that if you just take the idea that an electron has a wavelength, and then you say the only orbits for the electron that are allowed are those that have an integer number of wavelengths, then you naturally get that only certain orbits are allowed, others are not. That fits the data in exactly.
Right. So the obvious reason the electron is a certain distance from the proton is because of the fact that it's in tension with other electrons. That's the obvious reason. It's in a field that says so. It's just charge. It either moves into the charge or it doesn't. And the only thing that where any of this movement stuff is probably at play is with a neutron. A neutron probably has an electron that's in motion, or the whole neutron is spinning. But you don't need spin, you don't need momentum in any of the atom structure because you already have the tension between the ping pong paddles. They're attracted to going in, but they're repelled with each other, so they're in a balanced equilibrium between the two pressures. The pressure to go in, the pressure to stay out.
The way that Bohr had wanted to. So Bohr had this phenomenological relationship, right? Some certain electron energies and orbits are allowed, certain ones are not. De Broglie is trying to explain it by saying the reason why you get these energies is because electrons are waves. So from both sides, our classical intuition is being attacked. We thought that matter was particles, and we thought that forces were fields, and we're realizing that matter has wave or field-like properties.
So there's, like I said, they're saying the electron is somehow waving its way around, and it's a full wavelength of distance circle. And if I go one wavelength different, it's somehow one extra wavelength, I'll be in a new orbit. Yeah, that doesn't happen. The distances are much greater than that.
And waves have particle-like properties. Okay. So it was all put together. I'm going to, again, because we're not being historical, the first really full-blown quantum mechanical theory was called matrix mechanics. It came from Heisenberg, Born, and Jordan. And physicists didn't like it. Like Einstein said, this is just mathematical jiggery-pokery. Like, I don't understand what they're saying. This is Einstein saying, this is too mathematically complicated for me. But very soon after.
Right. That's sort of the irony of all of this whole subject, is Einstein was so guilty of the same crimes he accused others of. But yes, I say he was at least... He at least he was honestly critiquing other people. He maybe didn't honestly critique his own book BS, but he, in a sense, did. I mean, look, the fact that 2 years before he died, he said, I've been studying photons for 50 years and haven't improved my understanding one iota. So he's basically saying, I still don't understand this shit.
That picture came along. Schrödinger comes along with his picture of quantum mechanics. And it turns out to be equivalent. Schrödinger and Dirac and others show that these two ways of doing quantum mechanics are equivalent, but Schrödinger's way is just much more comfortable to physicists because it's...
Dirac is all full of antiparticles and a bunch of woo. So again, more made-up mathematical notions of reality that have nothing to do with anything physical or real.
Story of waves, not of matrices. Matrices are mathematical objects. Their physical meaning was not very clear. Schrödinger comes along with waves, and physicists knew what to do with that. They were very happy with the idea of waves. So Schrödinger says that we should have these things called wave functions. And he didn't even, as it turns out, the way that he thought about it wasn't exactly the right way early on, but still we keep the idea. And he had an equation, the Schrödinger equation, which tells us how the wave functions evolve. So what is going on? What's the difference here? I mean, de Broglie says electrons are waves, but he didn't give a dynamical equation for how those waves evolve. If you had asked, how do two electrons bump into each other and scatter off, he wouldn't have been able to tell you that, okay? The classical paradigm that we've been working with before is given juice by this idea that if you tell me the positions and velocities of everything in the world, then Newton's laws, or Hamilton's equations, or the principle of least action, or whatever, will tell you how to move them forward in time.
No, the more rational thing to do. See, that's where he just said the position of everything. You don't need everything. All I need to know is where the light bulb is. I don't need to know everything in the universe. I just need to know where the light bulb is, because that's where the field changes is being caused. It's by that light bulb. That source changes the field. The field doesn't magically change. The real items, the real things in the universe affect the change.
How to evolve them in time. That's the kind of equation you want to turn these ideas into a full-blown physical theory. So that's what Schrödinger gave us, and also what Heisenberg and Born and Jordan gave us. They gave us a way of taking initial conditions and being a quantum version of Laplace's demon, of saying from those initial conditions, what happens next?
Well, yes, and the initial conditions are everything. So again, they're equations that are absolutely useless. But you have to know everything to answer them accurately. And the less you know, the less you're going to get out of the equation. So it's just mush.
So Schrodinger's wave function, capital psi, the Greek letter psi, is a typical way of writing it. So for just one particle, let's just take one electron. We'll make the world more complicated later on. So it's a function of where the electron could be and when. So
where it could be. I mean, just right there, you're already saying, well, what's the point then? You're not going to tell me anything about where it is. You're just going to give me an equation that says it will be where it will be. If it's here, it'll be there. If it's there, it'll be here. If it's over there, it'll be over there. I mean, that's all it's going to tell you. It's going to tell you, I don't know where it is over here. Well, it's going to be over here, but it's also going to be, I don't know where it is over here. So, I mean, I already know that. It's the only way I could be doing this equation is I knew something moved. You're just telling me, oh, this ambiguous crap moved to over here. Oh, okay. I could figure that out without that little forky symbol.
Looks very much like a field on space-time, but there's subtleties that we'll get to, which is why we don't call it a field. We call it a wave function. That's what it is, or the quantum state. So AKA, also known as the quantum state. And just as a mathematical fact, at any one point, the wave function is a complex number. So this is a real number plus an imaginary number.
Well, I suppose this is as good a time as any to just say the hell with this, because it's just going to get into Hamiltonians and all this other wooey crap. So maybe we'll pick it up later or whatever, but you can see the dividing line. Okay, we've already decided energy equals, all these funky things. So energy equals lambda, and then lambda equals momentum, and these aren't equivalencies. They're proportionalities at best, but they certainly don't deserve any equal sign. Alright, so probably enough of a video. I mean, it's probably more than an hour and blah blah blah. But anyway, so the whole theory of quantum mechanics, this is how sloppy it is. There's no real cause and effect chain or logic chain that will be demonstrated here. It's just a bunch of, we speculate about something, we decide to write it into the truth, we decided to write it on the truth rock way, way, way before we had evidence to do that. Way before we analyzed any other explanations.